welcome to another Math with Taebyn. My name is Taebyn. I'm a pup, bark bark. And I hope you're all having a wonderful day. Today, I would like to talk a little bit about three-dimensional vectors. Now, this assumes that you already know things about two-dimensional vectors, what three-dimensional vectors are, basic integration, and to know that the position is the integral of the velocity. So things you learn, ideas you learned in your first calculus class. So hopefully you'll be able to follow along. And so what I want to talk about is a particular example of a nice way applications of three-dimensional vectors are used that you'll find very common in your calculus and physics classes. So here's what we want to do. We have a golf ball. An overall picture. I always recommend draw pictures always. It really helps you out, especially with word problems. So I'll draw this in a second, but just to read it, we have a golf ball. It's hit east with an initial velocity of this. So when I draw the picture, we'll see what this means. But this is basically the x direction is 50 meters per second, 0, and the y direction 30 meters per second upward. That's his initial velocity. We have a crosswind that's blowing from the north to the south, and it's producing a southerly acceleration of 0.8 meters per second squared. So part A is we want to find the position function. That says A, believe it or not. Find the position function, which we'll call r of t. So this will be a vector value function. In the end, we will have a three-dimensional vector where each component is a function that has a t in it. Not coffee, but t. So let's draw this picture and see what we're looking at. So I'm going to start off by drawing an XYZ axis, and we'll put this X. Here's Y, if you see Y, and here's Z. Z. And what's happening is you're starting at the origin, because everything starts at the origin, and we're going to hit it, and it goes in a, see, we're hitting it to the east. Oh, well, now we have to pick which way's east. You can pick whichever direction you want. You just need to make sure you're consistent throughout the whole problem. And let's just say the x-axis is east, and then that means that nobody eats shredded wheat. That means that the y-axis must be north. And then, of course, the z-axis is up. So we're hitting the ball in an east to the east. And then we have a wind. The wind is going from north to south at 0.8 meters per second squared. So that means that when you hit it, the ball is going to go like this and end up over here somewhere. Now, the position function will be able to tell us exactly where the ball is at any given time, and we'll use that information in part B. So let's think about this. Okay, magic of technology. Here it is, giving me room to write now. And there's where the ball lands when it hits the ground. This little blue right there. So we have to write down what you're given. Always, I say draw a picture, write down what you're given. Sometimes you might need to write down what you're trying to find out, because maybe you're not sure. And then probably you're told what you're trying to find out. So we are given what our acceleration looks like. Acceleration. Well, let's see. There is no, if you look at the, I'm going to point to you. If you look at the problem, there's no acceleration in the east direction, only in the north to south direction, and in the up and down direction, because there's gravity involved. Gravity. And you might remember from physics or calculus or wherever, the acceleration due to gravity is usually represented by g. And so, again, you just need to be consistent. Positive g means gravity's pulling it down. So that means if you were to go up, you're looking at negative g. So let's, the acceleration then is in the, remember, this is the east direction, that's the x component. So in the east direction, there's no acceleration. In the north direction, there is So we're going north to south. So remember, our wind is here, 0.8 meters per second squared. So since we're going north to south, and this is the north direction, this is a negative 0.8. And then, like I said, since down, gravity's pulling down, this will be a negative. Oh, right. So down, and so for our third component, we have negative g because we're hitting it up, right? And so g means down, so we have a negative g there. So we're given just in the problem, our initial velocity is 50, 0, 30. It's a 3. And our initial position, so that will be r of 0, is just at the origin. So we can use this. So we want to find r of t. All we need to do is integrate things, right? So we can find from our acceleration, we can find our velocity function. So we can use this now. Since velocity, if you remember, so calculus, physics, velocity is the integral of acceleration. And that's just because acceleration is the derivative of velocity. Really, all we need to do then is integrate the acceleration function. And you might remember, you just do that by integrating term by term. The integral of 0 is just a constant, so I'll call it C1. C1, yeah, you see it. And these will be different constants, generally speaking, so that's why we need to give them different names. The integral of negative 0.8 is just negative 0.8t plus C2. And the integral of negative g, and we'll put numbers in for g in a second, negative gt plus C3. Sorry for my horrible writing. I'm just a pup. I never learned to write too well. So we can now solve, just like any good initial value problem, we can now solve for C1, C2, and C3 using, I'll go ahead and label these numbers 1, number 2, number 3. From 2, again, there's nothing, no tricks here. It's just normal integration stuff, which hopefully you're familiar with. Plug in is 0, right? If you, maybe I'll do this down here. If you were to plug in a 0, you get C1 negative 0.8 times 0 is 0. So you end up with C2 in your second component, and then similarly C3. But then what we know from 2, whatever this is, it has to equal that. So we get that C1 must be 50. C2 is 0. C3 is 30. That was stupid. I know, Taebyn, why did you do that? I don't know, but that's what I do. I'm just a pup. So we have our velocity function. Okay, so let's go ahead and just put a number in for g now, just so that we have a number to work with. You might remember, since we're doing meters per second squared is what we were given, that means the acceleration due to gravity is the 9.8 meters per second. Okay, so that means that here we can put in a 9.8 for g. Now, okay, we need to find the acceleration. Okay, so we found velocity. Now we need to get to what we're trying to do and find the position function. Remember, we're trying to find the position function RT. So you do this exact same thing. Now that we found velocity, since velocity is the derivative of position, in the same way, our position function is the integral, just like we did before, integral of velocity. So, little exercise for you. See if you can do the exact same thing. What you should get is that, and there's no tricks. This is, basic integration. But what you should get is 50t Oh, and then, you still have to solve for your constants of integration. So I'm saying after you do, you'll get 50t for your first component, and you get negative 0.4 t squared. The constants of integration turns out to be 0 there too. After you plug in this 9.8 for g, you get negative 4.9 t squared plus 30t. So make sure you can do that. But in any case, there's our position function. Now let's see what we can do with this in part B. Again, magic of technology. Now we're on to part B. So remember, you land here. And so what this means is we want to know how far does the ball travel horizontally. That's a big word for a pup. It's this distance here. So this red is the distance ball has gone when hits ground. Okay, now mathematically, what does that mean to hit the ground? Well, it's going to hit the ground when the up is just 0. So that is when z equals 0. So once we've kind of logicked through that, we have our position function. Remember, this is the function that tells us exactly where the ball is at any given time. So the game plan here is to find out at what time does the ball hit the ground, and then we'll know the exact position. The ball hits the ground when z equals 0. So what's our z component? Or up component? So say when this thing equals 0. Now, basic algebra solve, you can use quadratic formula, factoring however you want. But if you solve that for t, you get t equals 0, which makes sense. That's when you start. You're on the ground when you start. So t equals 0 makes sense. We want to know the other value of t, 6.12 seconds. So it's taken 6.12 seconds to get to this spot, and we want to know how far is this from the origin. That's distance formula. If we look at this as a vector, that's the length of that vector. So we're looking for distance ball has traveled, I'll try and get out of the way of my own writing, horizontally is the length of that vector. Or just think this is from the origin. However you want to think about it, I'll just write it in a more mathy way, the magnitude of this vector, after the 6.12 seconds when it's actually hit the ground, which is, if you plug all these in, you should get 306 negative 14.98. And you're not surprised that the third component here is 0 because it's on the ground. It should be 0. And so if you do Pythagorean theorem, however you do this, it could be the square root of all these components squared. Don't forget parentheses. You don't want to pick up a negative sign here. And then, 0. But I'll write down 0 squared. If you calculate that, you get 306.4 meters. And so again, that represents this distance here. So there you have, there's a lot of really good ideas in here. Ideas of how to use vectors, how to use integration, sometimes differentiation, to help you just logic through and figure out things. I always recommend don't memorize formulas, understand how things work. And then that'll help you just remember formulas if you need one. And it also makes more sense because you can logic through problems like this and know what things stand for. So I hope you learned a lot from it. It's a lot of fun. As I say, it's a really good example of a lot of things. So if you have any questions, leave in the comments below. Now I'll try and get back to you. Otherwise, thank you for joining me with this math with Taebyn. See you next time. Bark, bark.